Oh my God. Wow. No way.
Guys must have had a good weekend. All right, so I think we should probably start class. I suspect. No. No. All right. Okay. So, if you guys have been feverishly F5ing my complex analysis notes to see if I've got them updated, then you would have noticed over the weekend that I caught up to where we are in class, and I posted a bunch of new homework exercises. I have one more section. I have a lot more I could say about conformal maps, but from a realistic perspective with the scope of the class, I can talk about basically one more application. The application I'm going to choose is going to be what's called the standard upper half-plane solution, which is what I'm going to talk about. If anybody in here is interested in how this goes beyond where any of the topics in this class go beyond what I can do, it's possible that I can run, what I did when I taught 550 last year was I ran a 2-credit sort of seminar class with like no homework or anything, but just sort of topics for, I think I had like 12 people in it. So I ran that in the winter and actually in the spring just so I could throw more ideas in. So if there is interest in that, you guys want to see more of this and you want to do it in a super low commitment environment, the commitment is, it'd be cool if you showed up, but there's not going to be any, I'll give exercises, but there won't be anything graded. You just come to class and hang out and do, but I have things I have to get through in here, so it's hard to do depth. So if you want depth and you want to keep going, I can do independent studies or I can do a seminar. So you guys can let me know at the end of the quarter if you're feeling that or not. If you're interested in how I'm making the visualizations that I've started to put up in the notes, that's in Mathematica, which you all have access to for free. If you've never bothered to download it and install it, you do have it available. The same tricks I'm using in there can be used in other languages as well, but Mathematica has a very nice complex analysis visualization package. So, and if you want to learn how to use Mathematica, I'm teaching 350 in the spring. You can drop in and hang out with me. And if you don't want to take my class, I have a whole set of notes from the last time I taught them how to use Mathematica. Okay, so my plan for the week is probably I'm going to get through this today and tomorrow. If I get through what I want to get through today, then I will probably dedicate Tuesday to a working day in class, or Thursday. It depends on how far I get. But there's definitely a day for working on problems this week. This assignment might be slightly longer because there's more ideas to cover, but not too much. But at least I want to give you the opportunity to work on these. And then maybe I should give you an exam at some point. It's kind of part of the deal. But not like an in-class test. It'll be a take-home thing. I'll write up some, what's that? Oh, no.
You said not to do that last quarter.
Not to do what?
Not to give a take-home.
Well, but the difference was in the last quarter I couldn't do a take-home exam because that's a GE class with like really strict content requirements, right? I have to teach you guys the techniques of complex integration, and so if I have something that like photomath can do, I have to write questions that are really hard, right? Here, I can ask harder questions and then just say, go think about these for a week or something like that. With the deal being that if I'm asking you harder questions, I'm expecting sort of, some effort to engage with it. I'm not just going to be, dropping Fs on people because the problems were hard and you couldn't figure it out or something like that. It's like, I haven't decided what the rules on collaboration or groups are yet, but it wouldn't be surprising if there's some sort of collaboration involved. So we'll see. It'll depend on the difficulty of the questions, right? I want you guys to engage with this stuff like the way people really engage with mathematics, and engaging with mathematics at a real level is meeting with people and talking about what's going on and not sitting in a desk by yourself for 15 minutes grinding out integrals. So, okay, so we'll talk more about that maybe on Friday. So we're going to start today with what's called the standard upper half-plane solution, which I think I hinted at last time, but I'm going to start again here. So the idea is that in the same way that we had, when we went through the uniform velocity problem, we set up a uniform velocity on the upper half plane, and you can conformally map that solution to other sets to see what happens to the flow lines when you do that. So the uniform flow on the upper half plane is what's called a standard solution. You assume you've got one flow, it's parallel to the real axis, and if you can conformally map that, you can track what happens to flows to any other conformally related set. What we're going to define this time is something not in terms of Neumann conditions. So last time we talked about sort of a Neumann problem, sort of a Neumann standard problem. Where we started with a flow with flow lines that look like this. And then we noticed that you can conformally map the set that looks like this. So, that set and this set are conformal under the map z plus 1 over z. So that gets you from here to here. And so by precomposing the function here with the conformal map that does this, you get a function that takes this set, a harmonic function on this set. The idea is that this had the solution f of z was equal to alpha z. So if you calculated a function, say big F, which is equal to little f composed with the map z plus 1 over z, then you end up with a function that was harmonic on this set. And the same relationship with the streamlines. Right? So we transformed our standard solution into a new situation by using this conformal map. And what you got out as a result was that when you transformed these streamlines, they ended up looking like this. Right? So the approach was start with a known standard solution and a conformal map that relates the region that we have the standard solution on to a new region of interest. And then when you calculate the complex potential and you transform it, you end up with a complex potential for the original set. It's sort of the upshot of what we finished with last week. And that actually is what I'm up through in my notes now as to this point. So what we're going to do today is we're going to talk about the same idea, but we're going to start with a Dirichlet problem instead. So a problem where we set not... I guess I should say, why is this a Neumann problem? The condition here is that if you checked the flow du dn, so if this is the normal vector to the boundary right here, there's no flow across the boundary in this problem. So du dn, which was equal to the gradient of u dot n, is equal to 0 everywhere on the boundary because the flows were parallel. So nothing is coming across the boundary. This is a condition on the derivative, which is what it means to be a Neumann problem. A very simple Neumann problem. So here's our Dirichlet problem. So what we're going to be looking for is a harmonic function that has that's harmonic on the upper half plane and satisfies this set of boundary conditions. So we're going to cut the real axis up into two pieces. And we want it to satisfy u is equal to 0 on this side, and u is equal to 1 over here. And we're seeking a u harmonic on the upper half plane. So there are many solutions to this problem. One of the solutions that turns out to be a useful solution to consider is the one where if you take a point z in the plane, which is x plus iy, and you take this point down here where the conditions change, and you draw this line and you calculate this angle. There's a couple of different ways of writing down theta here. The first is you can think of theta as being the arctangent of y over x with attention paid to the values that the arctangent is producing. Or you could think about theta as being the argument of the function z. So this is what you use when you want to compute with it with a function of x and y. So if you're thinking about it as a harmonic function in terms of variables x and y, this is what you think about it when you're thinking in complex analysis. So the claim is that we went through last time, which I won't review the details, but I'm trying to remind you, is that the function f of z is equal to 1 over pi I times the log of z where just you choose the branch of the log that you're working on so that the branch cut stays out of the upper half plane. The argument is, one, this function is analytic. Logarithm is analytic as long as you stay away from its branch cut. Two, that the function that we're interested in here is u is equal to 1 over pi I theta. That this function is the real part of f. And to be the real part of an analytic function is to be harmonic. So because u is the real part of an analytic function, yep. 1 over pi. Oh, this is, yeah, sorry, 1 over. Yeah, my bad. It's got to be real. So yeah, you don't have an I running around your harmonic function. Yeah. Thanks. Nice catch. Right. So this function, because it's the real part of an analytic function, is harmonic. I think I asked you in the exercises to go through and verify that more directly. And then it turns out that if you trace through what happens as you let the z's go to the boundary here, it's not hard to see, since it's an exercise, I'm going to leave it to you to do. At least in this case, it's not hard to see that as you drop this to the boundary, you get the exact condition that you want. That this function agrees that this has the property that u of x0 is equal to 0 when x is positive, and u of x0 is equal to 1 when x is negative. And this, I'm using this in the sense of as you limit to the boundary here. So you're harmonic on the upper half plane, and as you drop to the real axis, you actually get the real axis conditions that you're interested in. Okay. So, I mean, the thing is, at 0 itself, the log isn't defined. You have the branch cut lands at 0, and since it's in the boundary, you just neglect it. And essentially what's going to happen is if you actually trace through what's going on here, there's going to be some sort of rotation point set up here. And in fact, you can see, just from the definition of the function, without calculating anything, you can actually guess what the flow lines corresponding to this must be. So if you have a harmonic function, so let's suppose that we start with the upper half plane, and we have the exact conditions that we started with. So here's u is equal to 0, and here's u is equal to 1. And we have the function u is equal to 1 over pi theta. Where are the lines of constant, where are the level surfaces for this thing going to be? What are you going to say?
Sorry, I was thinking where you.
I mean, yeah, right? This will be constant when the argument doesn't change, right? So if you give me an angle, this thing will be constant when the angles of the numbers don't change, right? So, what's that?
Those aren't the flow lines.
They're not. They're the potential lines, and we're going to show how you can think about what the flow lines are from the potential lines.
Right.
Yeah. I'm going to say, I'm trying to show that you can recover the flow lines from the picture, at least intuitively, without even having to refer to the harmonic conjugate and calculating those level curves.
Are they circles? Like half circles?
They are.
Whoa.
Yeah, because what happens here is you end up with these lines. These are the places where u is constant. Right? U will be constant whenever the x and y's that you're feeding it are of constant angle. Yep.
Do the boundary conditions give a direction?
They do give a direction. So when you calculate the gradient field here, you can see, so now, here's where you have to be careful about mathematical interpretation and physical interpretation. The mathematical interpretation is going to say that if you have the function is equal to 0 over here and 1 over here, the gradient should be pointing in this direction, right? The gradient field, which will be perpendicular to these things, is pretty easy to draw because the gradients will look like this. So each one of these is a gradient of u. And if you calculate the streamlines for this function, you get, let's see, what color have I not used? How about red? So what that's going to tell you is that the streamlines look like this. And mathematically, the streamlines do this. Because mathematically what's happening is the gradient field is sending you from low values to high values. The physical reality is that heat flows from high to low, right? So heat energy flows from high to low. So when you put the physical interpretation on this, if you were describing heat, which is one of the contexts where this comes up, then heat follows the negative gradient field. So you just impose a negative sign if you want to be physically accurate. And if you're in electricity, even though it goes backwards because they screwed up when they defined the electron and put the negative in the wrong place, like the arrows are correct because of a double mistake. And if you didn't know that electricity is defined backwards, you should go look at it sometime. Well, okay, yes. If you're doing theoretical electricity versus actual physical electricity, they're very different in the way that they talk about it. Okay, so this solution is the basis for a whole library of standard solutions to, specifically these show up in this flow of heat, oftentimes, because this gives you boundary conditions that you can hold, and it gives you a pretty physically reasonable thing here, which is that, if you imagine heat this is heat, you've got something at heat 1 or temperature 1 and something at temperature 2. These represent the sort of flow lines of the heat in sort of an ideal infinite plate. Now, why this solution instead of others? You have a question?
I have a question on that.
Oh yeah, please. I'll take your question, and then we'll talk about why this solution is useful.
This is a vortex, right? If you think of it from a physical perspective.
Yeah.
For like half of one, so if you vortex, you put the branch kind of where you want it to overlap, right?
Yeah. Yeah. So typically with these, you can, because this is not part of the domain, see the thing is log doesn't even extend continuously here, so normally what you do is you just put it down here or something to get out of the way mathematically, right? If you have a physical scenario you're trying to model, then you got to be a little bit more careful, but for us, as long as it pokes out down here somewhere, it's not actually interfering with extension by continuity to the boundary. Does anybody have any idea why? Now I'm telling you that this is not the only solution to this. Why would we pick this one? What's one justification for choosing this one? How does this behave as z goes to infinity? What is the behavior of this function? You let x and y sail off to infinity. You have constants here, right? This is a bounded function, right? There's bounds in the function because you're defining it in terms of the arctangent, right? Arctangent is a bounded function. On both sides, right? Arctangent's trapped. And so that means this, in a lot of physical scenarios, you prefer to work, say you conformally map your upper half plane to a disk, and you had an unbounded function. Well, if you were unbounded on the upper half plane, you would also be unbounded on the disk that you map to. And unbounded amounts of heat trapped in a circular plate is not usually considered to be physically realistic. So there is some choice to be made in terms of which solutions are the ones that are selected. This particular one, that's one of its features that people like.
How is this bounded?
Well, how is u a bounded function? What's the largest value that u can ever take? What's the largest value the arctangent can ever take?
1.
No.
Or no, you can take 1.
Well, yeah, u, right? Are you sure?
1. When you plug in, it's.
I'm sorry, I meant like as you run off to infinity is what is the thing I'm trying to, like, to be an unbounded function, really what we're concerned about is, okay, so you're 1 here and you're 0 here, so locally you're going to be trapped by that, but the only possible place things can go wrong is if you sail away to infinity. So as you run away to infinity on the complex plane, you're either sending y to infinity or x to infinity, which means you're either tending to 0 or you're tending to pi over 2.
Okay, yeah. Okay.
Right? So it means that, like, at the other place that this hits the boundary, that you're still bounded.
But that's since the angle is bounded, not necessarily u.
But how is u defined?
Okay.
right? U is the angle with this modification factor to make sure that like when we throw it in here, everything works out so the boundary conditions link up.
So it's bounded by one half, basically. Even though it attains 1.
Yeah.
Okay. Sure.
Yep.
This is just more of an applications question. So in electricity, would that be 2 charged plates, or what would this model?
Okay, so electricity, normally the way that you, okay, so yes, that is what it would represent, would be 2 charged plates. And, but normally when you're setting this stuff up to model electricity, the normal model you begin with is with point charges. And then you're looking at, actually the main tool that you use when you're looking at point charges is that circle inversion theorem. Because you say, oh, there's a point charge here, it must have sort of an anti-point somewhere where that field collects, and so you put a virtual point at the reflection point, and then you trace through what the field lines would look like. I just didn't want to bring all that language in because this is not a physics class, and like, you know, even though that stuff is cool, that's all I'd be talking about for a couple of days. So. Okay, so what we want to do is we want to take this and we want to beef it up. So it turns out to be the case that one way that you can beef that up is you just break up your axis into more pieces. So what if I give you this one instead? What if I said, okay, there's a point at 0, and a point at 1, and a point at -1. And now I break the axis up into a chunk that looks like this, and 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 I give you a z. So let's actually suppose here we've got, I don't know, I think I set up a baby problem here, 10. So here I want you to be 10, here I want you to be 0, here I want you to be 10, here I want you to be 0. My boundary conditions. Yep.
If theta is bounded about by pi over 2, doesn't that restrict our theta to be only dealing with the first quadrant?
No, because you can you can use the argument to rotate its domain. This is all built out of the arctangent.
Oh.
The arctangent is just our computational formula. It's an argument. We've selected the branch of the argument that we want to use. And so normally what we do is we select the branch that runs from, say, like pi over 2 to, or, you know, so, to get all the way around to like 3 pi over 2, for example.
Got it,
Right?
okay.
So minus pi over 2, 3 pi over 2.
Okay. That makes sense.
Now these numbers could be anything. Can we build out, like in this, can we somehow use the same idea here that we built out in the original case? So in the original case, we said, okay, there was a z, and we built this angle that was theta, and we said that u was equal to 1 over pi times the log times theta. The answer is, you draw lots of triangles. So theta 1, theta 2, theta 3. The idea here, physically, I think the idea here, as you're imagining, is the amount of each one of these pieces that z sees is dictated by the angle that it takes to that piece. So if you can imagine, what will happen if you drop z down to each one of these chunks? Well, as you get down in here, you're going to get some sort of averaging happening between the pieces that it sees, right? And so we need to set this up in such a way that when I'm over here, I'm somehow canceling out everything that came before. And if I'm in the middle, then I'm seeing equally kind of what's happening on both sides. So it's got to be some kind of averaging happening. So I'm going to write down the naive solution here. Well, maybe I'll ask you guys a basic question. If I was going to write this down, so I'm going to write down the function, and I want you to tell me how to compute it. You see if you can figure out why it is what it is. So u is equal to, where's my notes here? So u is equal to 10 plus minus 10 over pi times y over x minus 1 plus 10 pi. Is there an arctangent? What am I doing? skipping my arctangent. Y times x minus 1 plus 10 over pi times the arctangent of y over x plus negative 10 over pi times the arctangent of y over x plus 1. So my claim is that for this specific setup, this is a solution. It's an example of a much broader family of solutions. What are these things doing? These arctangents here, yeah? There's,
Little step functions.
yeah,
Real line.
you're sliding over so you can compute the arctangent from the place where the angle is actually located. So you can imagine, one way of thinking about this is, you're sort of imagining that, say, with respect to angle 3, that the triangle that Z is on looks like this. And so you need to modify the length of the x coordinate that you're pushing into the arctangent in order to calculate what the angle is. So this is just dumb right triangle geometry. But it is. I mean, dumb not in the sense of idiotic, but dumb in the sense of there's not a lot of higher thought here, right? You're just writing down a right triangle and doing tangent. Now that is a good question. So what are those doing there? So the model solution in this case looks like this. So write this model down. A, C1, B, C2, C, C3, C, theta 3, theta 2, theta 1. So this is the general picture. And the general solution looks like this. U is equal to C3 plus C2 minus C3 over pi theta. I got this backwards, hold on. I missed a page. Yeah. C3, C2 minus C3 over pi times theta 3 plus C1 minus C2 over pi theta 2 plus C0 minus C1 over pi theta 1. Why these combinations of coefficients? So the negative 10s here, the negative 10 and the negative 10 and the 10 and the negative 10, that corresponds to taking this equation that we wrote over here. I guess I wrote my angles backwards, so to make it completely agree, I should do this. So the coefficients that I wrote there correspond exactly to these coefficients that I've written here, but why the averaging? Because essentially that's what I'm thinking here is like somehow I have a C3 and then I'm subtracting C3 and then I'm adding C2 and subtracting C2 and I'm adding C1 and subtracting C1 and there's this C0 dangling off on the end.
What is the value already left that? Does it have to be 0?
All the way. Oh, there's a C0, which was right here. My bad. Yeah, there's a C0 too. I mean, 1, 2, 3, 4 regions. 1, 2, 3, 4 initial conditions is the idea. Yeah.
If you were to like evaluate each angle as its own center of its own plane, are you like subtracting one from the other?
You're basically like looking at the overlap between those things. It's like a superposition essentially.
Yeah.
So one way of looking at what's happening here is you're taking 4 copies. You're taking 4 copies of our original problem and you're just sliding them on top of each other. So you're saying, and you're choosing coefficients precisely so that when you drop the angles down to the origin, that the boundary behavior is correct. Think about what would happen if you took this angle right here, or this point, and you dropped it down to the boundary. What should happen at the boundary? It should have value 10. What is the argument at the boundary? What is the argument of theta 3, theta 2, theta 1, or 3, 2, and 1? 0, right? So what's the only thing that survives? The 10. How about if you were in this plate? What's the argument of theta 3 when you get to the boundary here? Pi. So you have pi, 0, 0. So it flips the sign of the, so essentially, the pi cancels the pi and activates the term, and then you end up like canceling things. So what I mean here is, if you came down to theta 2, if you were at this point, What's the value of u there if you actually put all the arguments in? Well, you're going to get the 10, and then minus 10 over pi times, that's this angle, but that argument now is, sorry, theta 3 was pi, plus a bunch of zeros, right? 10 over pi times 0 plus minus 10 over pi times 0, which is 0. So that term is there to cancel the next one. It's like a binary switch almost, right? As you slide down the line, the next argument becomes pi to cancel what came previously. Yep.
So is your whole thing, look at the boundary and see what happens, don't care about the rest of the domain?
Well, the rest of the domain, so like, I guess the idea here is it's easy. All we're doing here is we're extending the idea that the logarithm is an analytic function and has argument, under appropriate modification, it has argument as its real part, right? So the argument is a harmonic function. That's the assertion. The argument is a harmonic function. So how can we use the fact that the argument is a harmonic function to build a more complicated solution? We're saying use the argument 3 different times. So that's superposition in the sense of I'm saying the argument, if I slide it over here, is still harmonic. And if I slide it over here, it's still harmonic. So just block 3 of them together, and you still have a harmonic function.
Gotcha.
This will be harmonic because it's a real part of a log, and a real part of a log, and a real part of a log. So if you take this idea and you extend it up to n, or n, say n plus 1 boundary values, this is called the standard upper half-plane solution. This is a bounded harmonic function that agrees with these initial conditions at the boundary. And you can write down the complex potential associated with it, which is C3 plus C2 minus C3 over pi logarithm of Z minus, oh my god, I've mixed my A's and C's together here. A, yep, oh no, I haven't, Z minus A. Have I really, I got C's over here and C3's over here. You know what? I'm going to leave this for right now, and I'm going to try to rewrite this correctly. The idea is that the logarithms that are associated with these just correspond to the shifts in the angles. And since it's wrong in my notes, I'm not going to try to untangle it. Yep.
Does this work as your widths between your cutting points become very limited?
Yeah, so the thing is that when you do that, so one thing about thinking about here is how is this hooked up with the Poisson integral, right? Hold on. What's the confusion here?
If you want to know why it's pi in the tangent, I was trying to explain.
What the pi is doing. So the pi is just getting pi's out of the, it's to make the arctangent spit out integer values instead of things with pi's, right? Because when you're computing arguments, naturally there's going to be, when you're working in radians, there's going to be these natural factors of pi that show up. It's just a normalizing factor so we can set integer values instead of pi values.
Yeah, that totally makes sense. I'm just wondering why it's pi. Our floating point is pi, or negative.
It's because when you...
So, okay, so what is theta? What is theta 3 with respect to this point right here? Theta 3 is measured with respect to this point. What angle do you rotate through to get to that point with that center of rotation? It's pi, right? So essentially, what the argument is doing is it's saying, I rotated by pi units to get here. I have a 0 argument here because I don't leave the x-axis this correspondence to this point of rotation, and the same thing here, right? So the argument is 0. The argument is 0 because I haven't rotated, but here I rotated around to get there. And the fact that that happens in a predictable way makes the solution useful because it means you can sort of toggle these things on and off. Okay. So the question at hand is, what the hell does this have to do with the Poisson? Essentially, if you conformally transform to the disk, you'd be looking at a Poisson problem, right? Boundary values on the disk all set up, and you'd have that terrible integral to do. Yeah?
If this is the real part of some logarithm with the branch cut not at theta equals pi,
Yeah.
then why are we using pi as a normalizing factor? Why not like pi over 2?
Well, because like it's still going to be the case that you, as long as pi over 2 is in the range of what you're spitting out with the arctangent. I mean, you can do that. You can still treat these arguments as just, I mean, regardless of how you set it up, this angle and this angle are going to be pointing in opposite directions, right? Like, so we just set this thing up with the branch sticking out in a way where this and this are both contained in the domain and they're pi radians apart from each other. This argument, this will still work.
Okay, okay. I just need a complex one. Refreshing on how to make a branch cut change.
All right. I'm derailed now. Oh,
Sorry.
okay. No, okay. So the idea here is that if you actually, if you can write u as being the real part of f, where f is equal to c3 plus this pile of logs, right? So like c2 minus c3 over pi of log of z minus, say, a, c3 is over here, c plus c1 minus c2 over pi log of z minus b plus c naught minus c1 over pi log of z minus a. And the idea is because it's log, 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 you're just superimposing the original solution that we had just 3 times. Okay? Yep.
You need eyes in the complex potential.
You do need eyes in the complex potential. Because that flips the argument to the real part. Yep. Now the nice thing about this is, because of the existence of modern visualizers, you actually don't need to write down what once you have the fact that you've got this thing as the analytic function, if you want to see what's happening, you don't actually have to write down the u and its harmonic conjugate and then calculate level curves. Like that can just be done numerically. And in fact, I might have an example to show you what this particular problem looks like when you look. If I did this correctly, I stored my Mathematica file in here. I did, okay. But it's from the 4th. Is this the naive one? Okay. Okay, cool. Let me get this on so I can show you guys. Wait,
So-
it is on. Go ahead.
So what happens when you make those sizes very small?
Okay, so that's a really good question. So the idea is that will actually limit, so because the Poisson integral is running around in the background, so what you should be thinking here is that, that's not distracting at all. What you should be thinking here is that what's happening is you can make these as small as you want discretely, and you're still going to end up with a finite sum of logs, which can be thought of in sort of a like a linear combination superposition setup.
Yeah.
If you push it and you want those things to become infinitesimal, so you have some distribution of temperature instead, then you're back in the Poisson integral case. So the Poisson integral says, if you tell me a continuous function on the boundary, right? So to say infinitesimal would be to say to continuously define the temperature distribution. You would conformally map it back to the disk, and you would just solve that integral by saying, like, look, this is the boundary condition on the circle, run the Poisson integral, recover the harmonic function on the disk, and then come back.
Okay.
So you have 2 choices, right? If you're working in a discrete setup where you say, I've got like a simple plate with like 2 pieces and they're like these 2 different temperatures, or some like 3 pieces where I can describe that, you want to use this solution because it's computationally easier to handle that way. If you actually need to give a continuous distribution of heat, then you need to use the Poisson integral. But the benefit of doing this, as we'll see in a future example, is you can actually specify pieces of the boundary that are insulated and then work with the solution. So you could have temperature 1 over here, temperature 2 over here, and then put an insulated piece in the middle where no heat can flow through it, right? And then you end up with, that induces something on the flows, and this model actually is amenable to that. So pieces where you define the conditions, and then pieces where you say du dn is 0. Like, this works very well with that, yep.
So with the Poisson integral, do you need a continuous function? Like
You
the
do.
values?
Yeah, so the reason that you need that is because it's reasonable. The Poisson integral, okay. The Poisson integral only works with continuous boundary values. That's a lie, by the way, because you can actually use you can use distributions instead, which means you can use direct delta functions. If you really want to, you can put point masses on the boundary too. But yeah, so continuous functions and continuous distributions. Right?
But this lets you use discrete.
This lets you sort of work discretely because you're saying solution plus a different solution plus a different solution. This is like the solution to differential equations, right? When you solve a differential equation, you get piece 1 and piece 2. What's the general solution? Glom them together. It's exactly what you're doing here, because you're saying the solution to this is piece 1 and piece 2 and piece 3. Glom them together, and you get the solution of the general scenario. I have vector fields on my head. Okay, so that is a visualization of the streamlines for the standard solution that we started with, where you had a boundary value. Remember, they point the wrong way for heat. We have an initial condition of 0 set up over here on the positive real axis, and a condition of 1 on the negative real axis. And all I've done here is you can actually see this is going to be the next solution, because that's the function I just wrote over there. So what's happening is this is the gradient field for the harmonic function that dictated this flow. Yep.
Is length intensity here, or is density there?
It's length, I think, the way Mathematica does it. Although maybe they changed and Mathematica normalizes all their vectors now.
Yeah,
I don't. The thing is, Mathematica is not stable version to version, so.
So the fact that there's like
It's not.
sized gaps in the middle, that's just an artifact of how
It's
the
the sampling.
right?
Yeah, it's the sampling rate. So it doesn't sample uniformly. Okay, so here is what the solution looks like in that second case. So this is a vector field. You can't see it. So this is the scenario that we drew on the board over there, where we have a piece. So what do we have? 10, and then 0, and then 10, and then 0. So this piece was at temperature 10. We have a piece at temperature 0. We have a piece at temperature 10. We have a piece at temperature 0, and a piece at temperature. Sorry, I got these backwards. I was going to draw on this thing. Everywhere the arrows are going down, it's 10, and everywhere they're coming out of, it's 0. And so this, you can already see that you can get some pretty complicated behavior just out of this really basic scenario here, with like the sort of boundary conditions. And so if you made little tiny boundary conditions, you're going to get a really weird like superposition of vector fields. This was before I figured out how to do this in the more elegant way. So I actually computed, as I will have you do in the simple case, I actually computed the harmonic function and its harmonic conjugate, and then I plotted the gradient field, which is not the right way to do it, by the way. But I was coding like a mathematician, where as long as the answer comes out the other side, then it's something happened. Okay. If you guys want this code, I'd be happy to, this terrible code. I'd be happy to share it with you. What's this one? Yeah, this was just me experimenting with different solutions to this thing. So in this scenario, you can actually look at the field and predict what the initial conditions must have been. So there must have been a 0 piece here in the middle, and then 1s out on the sides. Yep.
How do you tell if it's like the number 1 through 10? I know that's just arbitrary.
No, you can't. I mean, the only reason I can say what's happening here is because I used 0 and 10, right? So if you actually start making the numbers vary so that there's not just 2 different magnitudes, but like really different scales of magnitude, the way that it's not going to be symmetric, and you're going to get pieces that are really pushing out heat. It's going to be flowing like almost vertically out. And places where there's very small differences between the initial conditions, you should see much more subdued radius of rotation around those angles.
If it was the same number for both sides, 10 versus 1, would you have longer lines for 10?
Yes. I mean, if Mathematica is producing its vectors where you tell it that you want vector length to represent magnitude. So Mathematica's got a couple of options. You can tell it, this is just the stream plot, so it's actually not the vector plot. So this is just direction. If you tell it vector plot, it will give you the length of vectors corresponding to, or color of vectors corresponding to magnitude.
Are these the streamlines or the level sets?
These are, you should think of these as indicating the streamlines. Yeah, not the level sets. The level sets are orthogonal to these. Yeah, all of these are stream flows, right? Or the depictions of the streamlines of the heat flow. So the level curves of the complex conjugate, or the harmonic conjugate. And then where we're going to go with this, oh yeah, here's where I figured out how to do it with complex plot. Right, so here's the more elegant way of doing it, which is you plot the complex potential function, and you ask it to compute level curves of the imaginary part directly, and this is what you get. And what I want to show you next time, since I ran out of time here, is, well, one, I really hope that it's clear that all that's going on here, the only thing that's going on here is we started with something that looked like this. 1, 0. We said that a function that works on the upper half plane here is u is equal to 1 over pi angle of theta. That has flow lines that look like this, and all we're doing is taking that solution and moving it around on the axis and then adding them to each other, and this is the result.
That's only one solution that works for those others, right?
There are lots of solutions to this, yeah. This is a physically reasonable one in many, like this is sort of your in the same way uniform flow is reasonable but also really naive. This is reasonable and naive in the same way. It's just easy to demonstrate the theory of what's happening here. All right, so where are we going with this? We are going to take our complex, this is the result of taking a problem on the disk, or on the upper half plane, and then conformally transforming it to a disk. So you should imagine here, if I started with that picture, and I conformally transport it to the disk, I get this picture. Yep.
How many unique families of your choice of what families are there?
I don't actually know the answer to that. I suspect it's probably infinite, but I don't know, I don't know on what order, right? Normally the way that engineers and applied mathematicians approach these things is they identify physically reasonable or useful solutions that model some phenomenon, and they just give that a name and only work with those. So that's outside of my domain of knowledge. I'd be happy to look up the answer to the question. So anyway, this is where we're going with this. This is the last idea from this chapter is how do we start with simple scenario like this and then map the upper half plane to the disk and end up with a picture that looks like this. So these are the flow lines of a disk where you say temperature 1 on one side and temperature 0 on the other, and how does heat flow from one side to the other. Yep.
Is the fact that the flow lines extend to outside of this just that?
It's an artifact of the modeling,
Yeah.
although what that also represents is if you had mapped to the outside of the disk instead, you actually get the picture. Suppose you had a plate with a hole punched out of it, and you like a metal ring, and if the metal ring was set on top of a metal plate, that would still represent the way heat was flowing away from the ring in some sort of idealized way.
What are the colors?
So the colors here represent something about the magnitude of the function that you're, so like when you do a complex plot, the colors, I think in these plots, they're measuring the argument of z. Yeah, so if you actually plot this in a surface plot, you get it's flat here is what it's showing you, right? All right, see you guys. Yep. Wait, hold on, let me kill my camera first.